There's pictures of Henderson-Hasselbalch. A lot of people talk about Henderson-Hasselbalch, but they don't usually see their pictures. Woohoo, power of the internet. But anyway, let's say that you and I are in the lab. We want to create a buffer with a pH of 4.30. So if you have a pH of 4.30 that you want, that means that hydronium, which is 10 to the minus pH, should be about 5.0 times 10 to the minus 5 moles per liter. Okay, so we look in the stockroom and we find that we have several choices. But of the choices we have, we would like hydronium to be about equal to Ka or pH about equal to pKa. Because remember, HH is all about pH equals pKa plus log base over acid. And if you start with a pKa, which is close to your pH, that'll be a good start, and then you can fine-tune the ratio from there. But if you only have Ka values, then you want a Ka which is close to hydronium. So in our problem here, we want a pH of 4.30. That's a hydronium of 5.0 times 10 to the minus 5. So what we would like to have is a pKa close to 4.30. And if you only have Ka values, which happens a lot, we would like a Ka close to hydronium, 5.0 times 10 to the minus 5. So the closer you can get your chemicals to those Kas and pKas, the better. That's kind of what it comes down to. So in our stockroom, we find these three buffer combinations. All right, the stockroom never has quite what you want, but these are the things it has. Hydrogen sulfate and sulfate is a weak system. Ka 1.2 times 10 to the minus 2, and if you minus log that to get pKa, 1.92. And you can see there's acetic acid and acetate, and finally the last one is hydrocyanic acid and cyanide. That's a dangerous combination, by the way. We would want to make sure we use gloves and all that kind of stuff. However, it is a viable buffer source, and you can see the Ka and pKa. So hopefully you can realize here that if we want a pH of 4.30, we want a pKa as close to that as possible. And in this list, definitely the acetic acid acetate combination is closest to 4.3. 4.74 versus 4.3, that's closer. The first one, the hydrogen sulfate sulfate, would be probably more acidic, and the last one, HCN, CN-, that would probably be more basic. Now, if you had Ka values, we want 5.0 times 10 to the minus 5 to be as close to our Ka as possible, and that's obviously closest to, again, the acetic acid. The first one would be too big, and the last one, HCN, CN-, would be too small. So we definitely want to have the acetic acid acetate combination here. That's going to give us a system which is closest to our desired pH level. Equal moles of acetic acid and acetate would create a pH equal to pKa, 4.74. But we want a pH of 4.30. So that means that we want a more acidic buffer system. So it would be nice to know the ratio of acid to base needed to get the buffer to 4.30. So again, that's where pH and pK would be the same if the acid and base ratio were the same. The base 10 log of 1 equals 0. So pH equals pKa if the acid and base concentration is the same. But we don't want that to be the case. We want a more acidic pH. So it's not too hard to figure this out. And there's different ways to do it. So one way to figure this out is to go back to the Ka expression. Ka equals hydronium times the conjugate base divided by the acid. And if you rearrange this for the acid concentration, hydronium, that's going to, which is 5.0 times 10 to the minus 5, that's going to equal the acid over base times the Ka, all right? And what we want to do here is we want to find the ratio of the acid to base. We want to find this part. So what we'll do then is we'll take the hydronium, 5.0 times 10 to the minus 5, and divide by the Ka, 1.8 times 10 to the minus 5. And so if you do that, you end up with a ratio 2.8 to 1. And so what this tells you is that for every mole of base, sodium acetate probably, we'd put in, we need 2.8 moles of acetic acid. So we need 2.8 moles of acetic acid for every 1 mole of the base we put in. So if you put 0.1 moles of base in, you'd put 0.28 moles of acid in, and you are good to go. Let's say that we have 0.10 moles of sodium acetate and we have 0.28 moles of acetic acid. You should have a pH of 4.30. And that's kind of the idea here. Once you find the ratio, in this case it's acid over base, you can find then the ratio you need of the base to the acid, acid to the base, stuff like that. Now, to be honest, I probably would have used the Henderson-Hasselbalch equation here because I'm just the HH guy. But anyway, you could also use that pH equals pK plus log base over acid. So pH 4.30, pK 4.74 plus log base over acid. So 4.3 minus 4.74 gives you minus 0.44. You want an anti-base 10 log to get rid of that log part right there. So 10 to the minus 0.44 gives you 0.336, and that equals the base over acid ratio, but we want the acid over base ratio. So I would take the inverse of both sides. I would invert it, and that means go 1 over 0.36, that gives you 2.8, and 1 over base over acid is acid over base. So that's another way to find the acid to base ratio, and either way is fantastic. So at this point, I think it's cool to practice to make sure that you know how this works out. So here's an example of a buffer you can make: 8.4 grams of sodium hydrogen carbonate mixed with 16.0 grams of sodium carbonate. And notice here the hydrogen carbonate has more hydrogen than the carbonate, so the hydrogen carbonate is the acid and the carbonate is the weak base. And from these numbers and the Ka for hydrogen carbonate, you can calculate the pH.
To prepare our buffer solution, we first weigh our conjugate pair, 16.0 grams of sodium carbonate, the weak base, and 8.4 grams of sodium bicarbonate, the weak acid. We dissolve these solids in 100 milliliters of water. The final buffer solution has a volume of about 120 milliliters and a pH of 10.5.
To solve this problem, I would first turn the grams of sodium hydrogen carbonate into moles. That's going to be the moles of the weak acid. I would then turn the grams of sodium carbonate into moles. That's going to be the moles of weak base. Henderson-Hasselbalch, pH equals pKa plus log moles base over moles acid. You can use molarity over molarity, and you can do that, but that would be extra work, so I don't recommend it. You do need the Ka here for the acid. You would need the Ka for hydrogen carbonate, which is on that table. But anyway, if you've done this all, then 10.50 should be your answer. If you don't get that answer, let me know. Reach out to me. I will try to help you to find the right answer. But this is a good way to check yourself. Make sure you're good to go. Buffers are really important in our bodies. All right, as an example of that, we're constantly breathing in oxygen and exhaling CO2. And the CO2 actually has a slight acidic effect. So CO2 in water makes hydrogen carbonate, which is carbonic acid in water, which is really what happens. That makes H plus and HCO3. So HCO3 minus. So exhaling CO2 is actually a way then to get rid of some of the H plus. It gets rid of some of the acid. And as you get rid of acid, it makes it more basic. Exhaling CO2 raises the pH, makes it more basic of our blood. And this is something that medical people can use to their advantage, stuff like that. So there's a lot of examples of this. In addition, our kidneys use buffers and all kinds of things. This is just a main one that people talk about. And I think you'll talk about more in biology too. But buffers are awesome. Needless.